Okay, so the last time I already guys showed you a quick demo of how we do an E2 elimination. And I said that E2 eliminations happen when you sort of have the conditions that allow for an SN1 reaction, but instead of a nucleophile, we used a very strong base. Note, strong base is very important for an E2 reaction. So just like an SN2, we usually prefer having, let's say, a primary or a secondary substrate. But note, even a tertiary substrate would undergo an E2 reaction, again with the keyword using a strong base. So let's recall how an E2 reaction happens. You have your strong base, let's say the methoxide ion, which looks like methanol but deprotonated. Okay, so since it's unstable, it's not a nucleophile but a base, it really wants a proton. It grabs again the proton of the carbon adjacent to the carbon with the leaving group. So the bromine is our leaving group, the adjacent carbon or the beta carbon has hydrogen, so that goes there. The bond to the proton becomes the new double bond here. And since this carbon cannot take 5 bonds, it lets go of that bromine as a leaving group. Now, again, recall, for an E2 reaction to happen, we need to have a very special type of stereochemistry that we call your anti-periplanar, anti-coplanar stereochemistry. And I said when doing an E2 reaction, it's very important that you use Newman projections. So you draw your Newman projections. So again, you have your strong base taking the beta plus hydrogen, the beta hydrogen's bond becoming a lone pair, and then the leaving group leaving. Okay, and again, anti-periplanar, anti-position in the Newman projection. And if you follow that, these two flatten out. So these arrows don't represent electrons, they simply represent movements. Okay, you form something like this. Okay, so if this was us looking to the front, oh, by the way, Me stands for methyl, Ed stands for ethyl. So you'd have my methyl on my right, my ethyl on my left, so on and so forth. You'd come up with something like this. So again, it's as if I was here looking. So methyl on my right, ethyl on my left. Ethyl on my right, ethyl on my left. Okay? Again, using a Newman projection will help determine already if my product will be cis or trans, E or Z. So again, important for E2, strong base, anti-periplanar position, okay, leaving group, the alpha carbon has the leaving group, the beta carbon has your proton. And then Newman projection, flatten it out, then you get the right stereochemistry for your alkene. So again, more review. The same banana, same thing here. Okay. Special notes on the E2 reaction. Since you do need an anti-periplanar position, let's say you have a cyclohexane system, okay? The only way to achieve that anti-periplanar position is as if, or is when, your proton and your leaving group are both on an eggshell position. Note that this means it needs to go into the high energy state or the unstable state if your leaving group tends to be bulky. Okay, so this is the form that will undergo each reaction. Note, if you have the more stable version of this molecule, your leaving group is in the equatorial position. This is totally unreactive because you can never have that anti-periplanar or anti-coplanar requirement for an E2 reaction. Okay, with that, let's try to solve this problem. Okay, which of these chemicals will react more easily or more quickly under E2 conditions? So you have methyl chloride, okay, or neomethyl chloride. Okay, guys, that's not, okay, a typo. It really is menthol, okay. It's a structure similar to menthol, like mint flavor. But instead of an alcohol, it's a chlorine. Okay, so it's not a typo. Okay, so how do we solve a problem like this? Okay, you look at your substrate. You have your leaving group, which is obviously your halide. Okay, what else do you have to consider? You have to consider the stability of these. Okay, you have to draw both of these in the chair position. Okay, and then for each chair position, you have to decide, will wedge mean up or down, and will dash mean up or down? So obviously, if wedge means up, then dash means down. And you have to convert everything to that position. And note that up or down does not change, only axial or equatorial, depending on the ring flip. Okay, so let's look at methyl chloride. Okay, you draw it in its chair position. So isopropyl is an up, down, methyl chloride is down. Look at the structure here. Up was wedge, down, dash, down, dash. Up, down, down. Okay? Now look at the neomethyl chloride. Again, for this demonstration, I defined up as the wedge position and down as the dash. So isopropyl up, chloride up, methyl down. Draw the chair, put them in the proper positions. Up, up, down. Okay? Now, the next step is to draw their chair forms or their flipped forms. Let's flip this one. And let's flip this one. Although I didn't show the flip here anymore. What you need to do is you need to check, okay, is my leaving group in the reactive position? Meaning, is it in an axial position where it can undergo the anti-periplanar position? So in this version, the chloride in the equatorial position. So this is actually not reactive. But all of the substituents are in the equatorial, so it's very stable. If you do the flip, however, yes, chlorine is finally in the anti-periplanar position to this hydrogen. Okay, they're anti-periplanar to each other. But the bulky group in the eggshell, the bulky group in the eggshell. So it's unstable. It doesn't want to exist in this form, but it's reactive. But look at neomethyl chloride. In this form, bulky isopropyl, it's an equatorial. Methyl group, it's an equatorial. The chlorine, however, is already in the axial position, which is reactive for E2. So it can anti-periplanar with this hydrogen, or it can anti-periplanar with this hydrogen. And so, with a strong base, sodium ethoxide, it can create this one, or it can create that one. Okay? So, of course, since this form is stable with the bulky groups in the equatorial, but my leaving group in the axial, it is also reactive. Dito may atraso. If it's in the most stable form, it's also unreactive. If it has to be in the reactive anti-periplanar position, then it's unstable because of the bulky groups being also in the axial position. Okay. Now, the thing about E2 or E2 reactions is that they are very messy and they create a mixture of a lot of products. Okay. When describing, however, elimination reactions, we follow a certain rule to be able to predict what major product we form. And that rule is called Zaitsev's rule. Okay, to form a Zaitsev product means that we form the more stable alkene product. And recall what alkene stability is. So the most stable alkenes are alkenes that have all 4 carbons with substituents. Okay? And the least stable alkene is therefore all hydrogens or ethene. Okay? So ethene is very unstable. All carbon, tetra-substituted carbons, alkenes, yeah, very stable. So take for example this this molecule. Okay, this is 1, 2, 3, 4, 5. Okay, 2 bromo, 3 methyl pentane. Again, E2 requirement, very strong base. So like sodium ethoxide. Note the product. One is a tertiary alkene, carbon, carbon, carbon. And another one is a primary alkene, hydrogen, 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 carbon. Look at the proportions. The major product is the alkene that had more substituents. Now, Zaitsev's rule is very important, but remember, the first requirement to predict the major product for an E2 reaction is the product that comes from having your leaving group and your proton in the anti-coplanar or the anti-periplanar position. Again, you'll have to do your Newman projections, put your leaving group and thus whatever proton you can on an anti-position to each other. Then, only then can they eliminate. Or in the case of a chair formation cyclohexane system, your leaving group has to be in an axial position, let's say axial up and axial down, and the proton to be abstracted by the base has to be in the opposite position, so trans to it, but also in the axial position. So if my leaving group was axial down, then the proton has to be axial up. Okay? So the first requirement always for an E2 is the anti-coplanar, anti-periplanar. The second way to predict the major product is following Zaitsev's rule. Okay? Now, here's an example of a problem that shows that E2 doesn't always follow Zaitsev's rule, and that E2 always first looks at the anti-periplanar or the anti-coplanar version. Okay, so I have your trans 1 bromo 2 methyl cyclohexane. I have very strong base potassium hydroxide, and I end up with an alkene. Now, if we followed Zaitsev rule, okay, this bromine and this hydrogen would eliminate to form an alkene here, okay, because this alkene would have one, two, three carbon substituents. It would have been a tertiary alkene. But let me erase everything. But this alkene product is actually just a secondary alkene. Because you have a carbon, carbon, hydrogen, hydrogen. Okay? So we didn't form the Zaitsev product. Okay? Which means this bromine left not with this hydrogen, but with the hydrogen here. Kaya dito siya. Okay? Why? The number one requirement for an E2 is your anti-periplanar position. This bromine is in the dash position. This hydrogen is in the dash position. Can two substituents in the same relative position, let's say both dashes or both wedges, can they ever be anti to each other? Okay. The question is, or rather, the answer is no. This bromine and this bromine, okay, sorry, this hydrogen, at the moment, one is in equatorial, the other one is in axial. Let's flip it. Now my bromine is in axial, okay. But now my proton's in equatorial. So they're never in an anti-periplanar or anti-coplanar position. But if you look at the proton here, okay, or here, it has two, you have two choices. Okay. If we ring flip, this proton goes up here, and this now is anti-periplanar to your bromine. So the bigs will get this will go here, this will go there, and now you get my alkene. So again, the most important for an E2 is to be able to get that anti-coplanar, anti-periplanar. And then again, you also have to use a strong base. So even if it's primary, secondary, or tertiary, most of the time, strong base really means E2, especially if your strong base is very bulky, like tertiary oxide. Primary, if it's not a bulky base, will still undergo SN2, but secondary and above, it will always go straight to E2. Primary, if I use a strong bulky base, yes, it will go to E2. Okay, so in a summary for E2, E2s always happen with extreme conditions. So high heat and bulky strong bases like tertiary oxide, but strong bases will also usually work for secondary and tertiary. Very important to have that anti-periplanar, the anti-coplanar arrangement. Okay, and again, to be able to determine the stereochemistry of your product, it's very useful to use Newman projections. And that last, although we can predict the major alkene of a reaction by following Zaitsev's rule, which is forming the most stable alkene or the most substituted alkene, in E2, we don't always follow Zaitsev's rule because again, we always have to get that anti-periplanar and anti-coplanar position first. Okay? Oh, okay. Now, E2 is sort of a separate beast from SN2s or SN1s. But the SN1 reaction actually has a twin or a Siamese twin, not an evil twin anymore, but a Siamese twin that always occurs alongside it. Okay? And these are the E1 reactions. So elimination, E1 unimolecular. So every time I have conditions that are perfect for an SN1 reaction, there will always be an E1 product that happens. So what again are the conditions that favor SN1? So we prefer having an extremely good leaving group because it has to spontaneously leave on its own and form a carbocation. Next, we have to have a substrate that can easily form a carbocation, meaning it's tertiary. Okay. And the only difference is, instead of having a good nucleophile that attacks the carbocation, now you'll actually have a base, or your nucleophile will act like a base and grab, okay, the proton instead. So in this illustration here, the tosylate group is an amazing leaving group, leaves, forms a secondary carbocation, but the secondary carbocation is right beside a tertiary carbon, so there will be a methyl shift. Okay, don't forget carbocations equals shifts. Okay, so this entire, sorry, not methyl pala, fucking shit, hydride. So methyl if it's beside a quaternary. Hydride shift. This entire thing moves here. Note there's already one hydrogen here. So now there are two hydrogens here. And I have a tertiary carbocation. Tertiary carbocation is very good. Okay. Now, if we followed SN1 conditions, okay, then SN1 reaction, let's say my methanol solvent, polar protic, which is very good for SN1 because you want to form a solvent cage around the carbocation. That same solvent can also be my nucleophile. Nucleophile attacks the positive carbon, in this case the carbocation, and forms a substitution reaction, substitution product. But if, okay, the nucleophile decided to act like a base, so in our case it's also the methanol, it can actually choose to get a proton again from an adjacent carbon, and that bond to the proton that was formerly there now becomes a pi bond, neutralizing my carbocation and now creating an elimination or an alkene product. Note the label. E1 reactions almost always follow, or actually always follow, the Zaitsev rule. E1 reactions do not have that anti-periplanar or anti-coplanar requirement. Okay? So, the thing about E1 is that they always occur together with SN1. They're siblings. Again, they're connected together. So that's why I call them Siamese twins. The nucleophile that could react with your carbocation is already basic enough, even if it's a weak base, to take a proton from an adjacent carbon, and that would create the E1. So they're always competing with each other. Now, sir, what if we used a strong base instead? If you use a strong base, even with SN1 conditions, yes, E2 immediately takes in play, or immediately takes over. So E2 is a very, very common and very aggressive mechanism. Okay, so E1 always occurs with the same conditions that SN1 has. So again, let's recall. Leaving group leaves on its own, create a carbocation. But now the base, instead of attacking as a nucleophile the carbocation, it will attack the hydrogen or a proton from an adjacent carbon to my carbocation and forms my alkene product. So again, unlike E2, E1 has no stereochemical requirements, no need for anti-coplanar, anti-periplanar. And at the same time, Zaitsev's rule dominates. So we always form the most substituted alkene that we can. How can we promote E1 over SN1? Okay, and here are the most important things. Heat. Heat favors elimination. So just like in your experiment, when you dehydrated cyclohexanol, we had to really use a distillation setup. Okay, next. Now, if I use a lot of strong base, I will immediately favor E2. But if I use strong base but in a very dilute amount, then we can still favor E1. Take this for example. Okay, methyl chloride. This is the unstable reactive version. But if we have a lot of heat and a high concentration of strong base, then we favor E2 reactions. If it flips, it forms the more stable form. Okay. We use a very dilute amount of base. So this is 1 molar, this is 0.01 molar. So it's a very dilute amount of strong base. And our solvent is polar protic, meaning we favor forming a solvent cage around our carbocation. And again, we use a lot of heat. Then we form our E1 products. Notice the E2 conditions, 100% of the product is the non-Zaitsev product. Okay? So the alkene formed here, because this is the only position where your chlorine and your hydrogen can be anti-periplanar. Your E1, however, has a mixture of two products, so it's messier. And the bigger percentage product is the one that actually follows Zaitsev's rule. So 1, 2 carbons, so secondary alkene. For the E1 conditions, I have a secondary alkene, but only a small amount, and my tertiary alkene, 1, 2, 3, as my bigger or major Zaitsev product. So more substituents on alkene, major. That's Zaitsev's rule. So a summary for the the E1 reactions is that it has exactly the same conditions for SN1. So tertiary substrate, polar protic solvents, but you just have to add more heat or add a dilute amount of strong base. And the key signature or about E1 is that it almost always follows Zaitsev's rule. Now, I want everyone to screen cap this slide. Okay, this is a flow chart that will help you determine as much as or as accurately as possible, or have a good sense of what reaction will happen based on your substrate, whether if it's primary, secondary, or tertiary, or okay, and based on your reaction conditions. So if you have a strong base, if you have a bulky strong base, if you have a good nucleophile, if you have a polar aprotic solvent or a polar protic solvent. Okay, so if you have a methylic substrate, then it simply means you either have an SN2 reaction or no reaction, depending whether or not you have a good leaving group or a good nucleophile. But for the rest, primary, secondary, tertiary, let's go through everything. If I have a primary substrate, and then I used a strong base as my nucleophile, and not just a strong base, but a hindered strong base, meaning it's very bulky, it immediately undergoes E2. So again, classic example for a bulky strong base would be tert butoxide. Now, what if it wasn't a bulky strong base? It will always undergo SN2. If it wasn't basic, it would undergo a slow SN2, which is still SN2. So even if I used methoxide or ethoxide as a base, since it's not bulky, it will actually go SN2. Okay? But that only happens for primary. If I use a strong base for any other of these substrates, secondary, tertiary, it automatically goes to E2. So let's check. Secondary, is the nucleophile a strong base? Yes, automatically E2. Tertiary, is my nucleophile strong base? Automatically E2. That's simple. Okay, what if my substrate was secondary, but it wasn't a strong base? Was it a good nucleophile but not basic? Then SN2. If it wasn't a good nucleophile, let's check. Is my solvent polar? If my solvent is polar, then you'd have SN1. And again, SN1 almost always goes with E1 products. So if you see signs of heat or trace amounts of base, then you favor E1. How about tertiary? If I didn't use a strong base, and then you see the solvent was polar, then you'd have an SN1 or an E1, and then you'd decide if it's SN1 or E1, whether or not you have, again, some high temperature, some heat applied, and trace amounts of base. Okay, so let's try this out. Here are some exercises that we can try together. Okay, so we can predict the mechanism. I have here a molecule, secondary alcohol, high amounts of acid, heat, and a distillation process. So what process do you think will happen? So let's go back to our table. Can Rx, or form a good leaving group, can what alcohol in an acidic medium with heat form a good leaving group? I think the answer is yes, because an alcohol group can be protonated by acid and turn into water. Now, what kind of carbon would it be? It's a secondary, so carbon, carbon, secondary alcohol. Is my nucleophile a strong base? No. Is my, do I have a good nucleophile that isn't basic? No, because the sulfate ion is not a good nucleophile. And it is, okay. And is my solvent polar? Okay. My solvent doesn't say, so we assume that this is my own solvent. So an alcohol is polar. So yes, we prefer SN1 and E1. Now, which do you prefer, or which will happen more, SN1 or E1? We have high temperature. So high temperature means E1. So yes, an E1 reaction happens. We get rid of this, turns into an alkene, and again, we form the Zaitsev product. So instead of getting a proton here, we take a proton here to form a tertiary alkene rather than a secondary alkene. Okay, let's try this one now. So, is tosylate a good leaving group? Hell yes. What kind of carbon is this? It's tertiary. Did we use a very strong base? Yes, we did. Sodium amide. So that automatically means we form an E2 product. And it's symmetrical, so it will all look the same. Okay, let's try this one. Okay, so everyone, let's go to the next slide. Tosylate, good leaving group? Yes. What kind of carbon is this? Carbon, carbon, hydrogen, so it's a secondary carbon. Is my nucleophile a strong base? No, it's not. But is it a good nucleophile that isn't basic? So the bromide ion is a very good nucleophile and it isn't basic. And also note, look, the temperature is cold, so it's not elimination. And my solvent is acetone, it's polar aprotic. So it really promotes an SN2 reaction. Easy. Okay, now try this on your own. So copy this, try to interpret the table using, okay, whatever skills you have. Note the substrate, note the reactants, note the solvents and whatnot. Okay? Pause this video, try it out for yourself, and then I'll give the answers. Okay. Bromide is a good leaving group. It's a tertiary carbon. Okay, so silver nitrate is not a strong base. Our solvent is alcohol, so it's polar protic. So yes, an SN1 and E1 product will form. Since it doesn't specify if it's hot or not, or if there's dilute base or not, okay, then you'll just assume that it favors your SN1 reaction. Now, here's the catch. Your alcohol solvent is actually a lot more nucleophilic than the nitrate ion and silver nitrate. That means that it's the alcohol that attacked the carbocation and not the nitrate ion. If you answered this with a nitrate ion attached here, that also would have been correct. But this would be the major product. SN1 formed an ether. What else do you notice? I have an alkyl halide, I have silver nitrate. Silver precipitates or takes away your halide group as precipitate. Okay? It takes that away. So it really does promote or favor the formation of a carbocation. Okay, try this on your own. Here's the table or the flow chart. Pause this video and try to figure it out yourself. Okay, so bromide, good leaving group. Secondary bromide. Is my nucleophile a strong base? No. Is it non-basic? Or is it rather a good nucleophile, non-basic? No. Is my solvent polar? Rather polar protic? Yes. So you'd favor SN1 and E1. There's a keyword here, warm, so you might expect E1 to also be favored. So you'd form a mixture of two. And if I replaced warm with hot, then probably this would have been the more major product. Try this on your own. So here's the table. Pause the video, try it out for yourself, and I'll give the answers. Okay. Bromide, good leaving group. Secondary. Was this the strong base? Not really. This is like sodium thiosulfide or sorry, ethane thiolate. So it's like an ethanol, but there's a sulfur instead of an oxygen. My solvent is polar aprotic. So good nucleophile. Yes. Is it basic? No. Solvent polar aprotic. So yes, SN2 is very much favored. So the bromide gets replaced by the thiolate or the sulfide group. And bromine used to be dashed, now it's wedged because again SN2 is a backside attack. Okay, try this one as well. Here, pause the video now. Okay, iodine, good leaving group. It's tertiary. Is water a strong base? No. Was my solvent polar protic? Yes, water is polar protic. So SN1 and E1 are favored. Didn't specify if any dilute base was used or if there was a high temperature, so we can assume we have a mixture of both SN1 and E1 products. Again, the E1 would always follow Zaitsev rule. So Instead of forming a double bond here or here, it formed a double bond here so that it could have a tertiary alkene. As simple as that. Last item, try this. Pause the video now. Okay, iodine is a good leaving group. Its secondary position was my nucleophile strong base, sodium ethoxide. And of course, we also used a lot of heat reflux. So yes, E2 is favored. Now, look at the product. It had to get a proton, and the only proton available was here. So did we form a Zaitsev product? No. Why? Because you couldn't eliminate anything here to form a tertiary alkene. There's no protons here. Remember, you need to remove a proton from an anti-periplanar position from your leaving. Okay. Try this now, and then pause your video. Okay. Chlorine is a good leaving group. It's primary. Is sodium ethoxide a hindered strong base, or is it a bulky strong base? No, it's not. Okay. So is our substance non-basic? No, it is. It's basic. So there will be some SN2 that forms. So the Cl gets replaced with an OCH3. OCH3. So you form an ether. Important word here though is that it's room temp. If this were a hot reaction, might have favored some E2 to happen as well. And this is the last, I think. Let's try this one. Which would react more rapidly in an E2 reaction? So how would you answer this? I want you guys to turn or create two chair drawings and then choose. Will wedge mean up or will wedge mean down? So if wedge means up, then this is in the up position. This is also in the up position. Up position, down position, and vice versa. What's another thing you have to remember? In a chair formation or in a chair position, the bulkiest groups want to be in the equatorial position. But what else now do you have to remember? Your leaving group, in this case iodine, can only react with E2 if it's in an eggshell position. So our goal here is actually to find a position in which your iodine leaving group will be in the eggshell position, but your bulky isopropyl group will be in the equatorial position. Okay. Oh, what are these two? Are they enantiomers? Are they diastereomers? Or are they the same molecules? Okay. So yeah, here's a little bit of a reminder from what I just said. And here are the answers. Okay. So in this form, the trans form, I have my iodine in the reactive position. So in an eggshell position for E2 to be able to have that anti-periplanar. But the isopropyl ends up being also in the in the eggshell position, which is not very stable. If I do a chair flip, yes, my isopropyl ends up in the equatorial stable position, but now my leaving group is in the wrong position. If I did the other option, the cis option, okay, my iodine will be in an eggshell up, and my isopropyl will be in an equatorial up. This is happy being in the equatorial. This may not be happy being in the equatorial, but it's reactive now or it's favorable now for the E2 reaction to happen. So anti-periplanar to this hydrogen or anti-periplanar to a hydrogen down here. Now you have something that's actually reactive for E2. So that's it. I hope you guys enjoyed or learned a little bit. I hope you guys also study your books. If there are any questions, you can Facebook me or we can have a live Q&A sometime when I'm back. Peace out.